Searching in linked list. Linked list also have a search speed of ON. To search for a value, we need to go through a similar process as we did with reading. That is, we begin with the first node and follow the links of each node to the next one. So just as reading, where we need to start with the first node, it's the same thing with search operation. Along the way, we inspect each value until we find what we're looking for. Here's how we can implement the search operation in Ruby. So along the way, we will be able to find that value, but we need to start with the first node. Now we'll call this method index underscore of and pass the value we're searching for. So for this searching, we use index underscore of name and with parameter value. We begin at the first node of the list. Current underscore node equals first underscore node. Just a moment, guys. There you go. So we start with the first node, obviously, and then current underscore index equals to 0. So we define two variable here that will change as we go to as we process our code. So this type of initialization of variables from node and index will be useful as well as later in the future videos. Begin, if we find the data we're looking for, we return it. So if current underscore node data equals to value we're looking for, return current underscore index and then end the loop. And then after that, if we didn't find it, otherwise we move on to the next underscore node. Current underscore node, so we change the variable equals to current underscore node dot next underscore node. Current underscore index plus equals to 1. So it simply means that if we didn't find that in the current underscore index 0, we increment the node until we find it. So end while current node. So if we get through the entire list without finding the data, we return nil. It means we didn't find the search value, and then we end this function. Now we can then search for any value within the list using list.index underscore of quote time. As you can see, the mechanics of searching are similar to reading. The main difference is that the loop doesn't stop at a particular index but runs until we either find the value or reach the end of the list. So again, the main difference is that the loop doesn't stop at a particular index but runs until we either find the value or reach the end of the list. So that's where the end while current underscore node. So if it's current underscore node is that next node. So it keeps iterating or incrementing. So that's what it means end while. And then we initiate that before as a variable. Now insertion. Insertion is one operation in which linked lists have a distinct advantage over arrays in certain situations. Recall that the worst case scenario for insertion into an array is when the program inserts data into index 0 because it's the beginning, because it first has to shift the rest of the data one cell to the right, which end up yielding an efficiency of ON. With linked list, however, insertion at the beginning of the list takes just one step, which is O1. So for the this is where the linked list shine over the array. It can access the beginning of the index in just O1. So say we have the following linked list. We have two blue, green, and red, and then the null. So if you want to add yellow to the beginning of the list, all we have to do is create a new node and have its link point to the node containing blue. So in our code, we'd also need to update the linked list instance so that first underscore node attributes now points to this yellow node. So we also need to update the linked list instance that we created so that its first underscore node attribute now points to this yellow underscore node. So first thing we have to do is that we need to create a new node and have its link point to the node containing blue. And then after that, we need to update the linked list or the first node instance of our linked list. Now, in contrast, with an array, the linked list provides the flexibility of inserting data to the front of the list without requiring the shifting of any data. How sweet is that? The truth is that theoretically, inserting data anywhere with the linked list take just one step, but there's one gotcha. Let's continue with our example. So here are linked lists now. We have inserted the yellow. So say we now want to insert purple at index 2, which would be between blue and green. The actual insertion takes just one step. That is, we can create the new purple node and simply change the blue node's link to point to the purple node as shown here. So again, the actual insertion still takes just one step. That is, we can create the purple node, which is here, and then simply change the blue node's link to point to the purple node. So here we just need to point it here. And then however, for the computer to do this, it first needs to get to the node at index 1, which is blue. So for the blue to connect to purple, the computer needs to start at the beginning and then get to the blue so that it can modify its link to point to the newly created node. As we've seen though, reading, which is accessing item at a given index from a linked list, already takes on. So this is the catch. If you're inserting at the end of the list, it may take you on as well because you need to go or start from the beginning of the index. Now, we know that we want to add a new node after index 1. So the computer needs to get to index 1 of the list. To do this, we must start at the beginning of the list. So we know that we want to add a new node after index 1. So the computer needs to get to index 1 of the list first. To do this, we must start at the beginning of the list, like what I've said. So here, first, and then blue, before we can add the purple. We then access the next node by following the first link. So here we're on the blue. Now that we found index 1, we can finally add the new node. So on average case, this might be better than reading all through until the end, right? Because that takes on. In this case, adding purple took 3 steps. If we were to add it to the end of our list, it would take 5 steps. 4 steps to access index 3 and 1 step to insert the node. So practically an end step for worst case scenario. So practically speaking, then inserting into a linked list is on. As the worst case scenario of inserting at the end of the list will take n+1 steps. However, we've seen that in the best case scenario, inserting at the beginning of the list is only O1. So here, scenario, inserting at the beginning, array, worst case scenario. So it's just an opposite of linked list. In the middle, they are the same in average case. So inserting at the end, best case for array, worst case for linked list. So code implementation. So you notice that for an array, in the previous arrays, we use pointer inside our code, which starts comparing from index 0. That's not an insertion, that's comparison. So usually for array, you can easily insert at the end, but you can't insert easily at the beginning. So that's the opposite of linked list, in which you can easily insert at the beginning while it's hard for you to insert at the end. So code implementation, linked list insertion. So let's add an insertion method to our linked list class. So we'll call it insert underscore at underscore index. So here we define insert underscore at underscore index with index and value parameter. So there's two parameter. In our search code, as you can see, we only have value parameter. So that's the difference of it in reading and searching. For reading, we only have index parameter. Notice the difference of the code in each operations. So we create the new node with the provided value. New underscore node equals to node.new value. So this we will put the value, the parameter inside here on this instant new underscore node. Now if index equals to 0, so if we are inserting at the beginning of the list, new underscore node dot next underscore node equals to first underscore node. So if index that we put in the parameter is 0, we will equate the new node that next underscore node equals to first node, and then self that first underscore node equals to new node. So that will establish that our new node is now the list first node, and then return, and then end. So that's the first if else statement in this function. Now current underscore node equals to first underscore node, current underscore node index equals to 0. Now we create a variable if we are inserting anywhere other than the beginning. So as you can see, guys, when we insert it at the beginning, which is if index that of the parameter that we want to insert the value is 0, have our new node linked to what was the first node. So the node link will be now equals to the first underscore node. So basically we're just connecting that to our new value or new index. Now after that, we will set that first underscore node equals to new underscore node, establish that our new node is now the list first node. So here, as you can see, set that first underscore node, which is the first underscore node that we initially created, is now equals to our new node. Now if we're inserting anywhere other than the code, we create a variable current underscore node equals the first underscore node, and then current underscore index equals to 0. Just it's the same with searching. So in searching, however, we define the variable first before we have the if and while loop, if else statement and while loop. While here, as you can see, we have the if else first before we create this variable, because this algorithm will then handle the insertion if it's not at the beginning. Now for while current underscore index is less than index minus 1, we do current underscore node equals to current underscore node dot next node, and then we increment current underscore index plus equal 1. Now first we access the node immediately before where the new node will go. So we access the node before the new node will go. For example, this graph here, we access this first, the blue, right? So we need to go first from the beginning to the blue before we get for the purple to be inserted here at the middle. So that's what that code essentially does. And then end. We end this loop, while loop, and then after that we clear new underscore node dot next underscore node equals to current underscore node dot next underscore node. So have the new node link to the next node. So we have the new node linked to the next node. So after that, once we connect the insert that we found the blue, and then we know where to insert the purple, we then link the purple to the next one, which is I think green or red. So new underscore node that next underscore node. So as you can see, this new underscore node that next underscore node is is the one we created, or where we input the value. We equate that to current underscore node dot next node, which is here in our while loop. So algorithm. Now after that, current node dot next underscore node equals to new node. So we modify the link of the previous node to point to our new node. So our previous node, which is current underscore node dot next node, here we link that now to our new node. So we modify the link of the previous node to point to our new node. So here where we connect this blue to purple. So as you can see, guys, it's an amazing algorithm. Then we end the function. So to use the method, we pass in both the new value as well as the index of where we want to insert it. Say list.insert underscore at underscore index 3 purple. First, we create a new node instance with the value provided to our method. New underscore node equals to node.new value. Next, we deal with the case where we're inserting into index 0, that is at the beginning of our list. The algorithm for this case is different than if we insert elsewhere into the list. So we deal with this case separately. To insert at the beginning of the list, we simply have our new underscore node link to the first node of the list and declare our new underscore node to be the first node going forward. So here, meaning this algorithm deals with the case where inserting into the first index, which is index 0, or at the beginning of our list. Now the algorithm for this case is different than if we insert elsewhere. So we deal with this case separately. To insert at the beginning of the list, we simply have our new underscore node link to the first node. So new underscore node link, we just simply have that to the first node of the list. So we just connect that new node to the first list of the list, as like for example, we insert this purple, we just connect this purple to this new node. So this box here, we just need to connect to that yellow. So that's how this code means. That's what it codes means. Of the list, and declare our new underscore node to be the first node going forward. So we then after that, after we connect that, we use that as the first node going forward. So yeah, here as you can see, new underscore node, which we created before. Here, new underscore node in this, new underscore node, which is the value we passed to the new underscore node instance. So we equate that as the first node and then return and then end the if loop. So the return keyword ends the method early, as there's nothing left to do. We've already inserted it. So the rest of the code deals with the case in which we're inserting anywhere other than at the beginning. As with reading and searching, we start off by accessing the first node of the list. Current underscore node equal first underscore node. So as with reading and searching, it's the same, right? We start with the value. We start by, it's not actually it's a variable, but at the same time, we're also accessing the first node of the list. So current underscore node equals to first underscore node. Current underscore index equals to 0. Since we're dealing with the case in which we're not inserting at the beginning, so we start with that. Since again, when searching and reading, or we need to search from the beginning, so we start with this, accessing this. So we then use a while loop to access the node just before the spot where we want to insert our new node. So in this case, purple, yeah, we access the blue first, right? So here is the code for accessing the blue. While current underscore index less than index minus 1, so the current index that we put there is less than the index minus 1, or the previous where we want to insert. For example, when it's 3 minus 1 or 2, it should do this: current underscore node equals to current underscore node dot next node, and then current underscore index plus equals 1, and then end. So essentially we increment until we get on that before index we want to insert. So at this point, the current underscore node is the node that will immediately precede our new underscore node. So at this point, the current underscore node is the node that will immediately precede our new underscore node. So in this while loop, the current underscore node will become, so as you can see, first underscore node, so it will increment until it become current underscore node that next node until it's index minus 1. So that's what this loop means. Next, we set the link of our new node, new underscore node. So after that, we get into that, we set the link of new underscore node to point to the node after the current underscore node. So after that, the new underscore node that we input as a value, we point to the node after the current underscore node, which is in this case on purple green. We point the purple to green in this code. So at this point, the current underscore node is the node that will immediately precede our new underscore node. And then after that, once we end that, the node we access that index and the value. Next, we set the link of our new underscore node to point to the node after the current underscore node. So we point that to the green. Finally, we change the link of the current underscore node, which again is to be the node that precedes our new underscore node, to point to our new node. So this is where we point I forgot again what is the color of that, the blue to the purple. So finally, we change the link of the current underscore node, which is to be the node, since we put that the current underscore node will be the previous one, is to be the node that precedes our new underscore node. So here, current underscore node that next underscore node is equals to new underscore node. So here, current underscore node here is the code for that. So it's pretty complex, but it's worth it to understand. Now, deletion. To delete a node from the beginning of a linked list, all we need to do is perform one step. So just like insertion, we just need to perform one step at the beginning. We change the first underscore node of the linked list to now point to the second node. Let's return to our example of the linked list containing values once upon a time. If you want to delete the value once, we could simply change the linked list to begin at upon. List that first underscore node equals to node underscore 2. When it comes to deleting the final node of a linked list, the actual deletion takes one step as well. So that's another difference. It's one step in array, but you may think that deleting is not a one step because it's an opposite of the array. But in here, we just take the second to last node and make its link null, so that it will be the new next or new last node. However, it takes n steps to even access the second to last node. So that's the catch. You need n steps because you need to start at the beginning to access the second to last node in the first place. since we need to start at the beginning of the list and follow links until we reach it. So situation, delete at the beginning, array, worst case. For linked list, that's its best case. Delete at middle, average case per vote. Delete at end, best case for array, worst case for linked list. So while deleting from the beginning or end of a linked list is a straightforward, deleting from anywhere in the middle is slightly more involved. Say we want to delete the value at index 2, purple, from our example linked list of color as shown in the diagram. Though deleting at the end and deleting at the beginning is straightforward, deleting at the middle is more involved. Say we want to delete this purple. So to accomplish this, we need to first access the node immediately preceding the one we're deleting, blue. So it's kind of like insertion as well. We need to start from the first node. For deletion as well at the end, we need to start at the first node. We change its link to point to the node that is immediately after the node we're deleting, which is green. So we just change this link and point this to green. So the following visualization demonstrate us changing the link of the blue node from purple to green. It's interesting to note that whenever we delete a node from our linked list, the node still exists in memory somewhere. We're just removing the node from our list by ensuring that no other node from the list links to it. This has the effect of deleting the node from our list, even if the node still exists in memory. So here's what delete operation might look like in our linked list class. It's called delete underscore at underscore index, and we pass in the index we're going to delete. So here it's kind of like the same as reading, where we pass the index. So for searching, we pass the value. For deleting, we also pass index, just the same as reading. So we start with an if-else statement. If index equals to 0, so if you were deleting from the first node, we create a different algorithm for this. So it's kind of like the same with insertion as well, because we searching, we start with an if-else loop before we define in insertion, we define new underscore node, which is the value at first, because we have two parameters. So after that, we have an if-else loop. And for reading and searching, we access the first underscore node, before we create our function. So that's the difference of deletion or delete function. So here, if index, we start with the if statement. If index equals to 0, simply set the first node to be what is currently the second node, or set that first underscore node equals to first underscore node dot next underscore node, return and end. Again, this is a Ruby code. And after that, we access a current underscore node equals to first underscore node, current underscore index equals to 0. Now first, while current underscore index is less than index minus 1, do current underscore node. So it's the same with insertion while loop, in which we access the previous node before the one we want to delete. So again, we need to start at the first index until we get to the blue if we want to delete the purple. So index minus 1 do current. So first we find the node immediately before the one we want to delete and call it current underscore node. Then after that, we set node underscore after node underscore after underscore deleted underscore node equals to current underscore node dot next underscore node dot next underscore node. We find the node that comes after the one we're deleting. So this is what this code means. And then current underscore node that next underscore node is equals to node underscore after underscore deleted underscore node. Then we change the link of the current underscore node to point to the node underscore after underscore deleted underscore node, leaving the node we want to delete out of the list. So again, this code, after that, it's just like a setting a variable here after those while loop. So two variables. First, we find the node that comes after the one we're deleting, and then we change the link of the current underscore node to point to the node underscore after underscore deleted underscore node. So that means we point that the blue to green since we delete the purple. So leaving the node we want to delete out of the list. So current underscore node that next underscore node. So notice what is this, which is this current underscore that next under is equals to node underscore after underscore deleted underscore node, which is like here. So it's kind of like the same code with our insertion code, I think. Yeah, insertion code. So notice that it's a huge pattern that we notice. Deletion and insertion has the same variable change at the end, or it's the same code they used to make the linked list deletion at the middle or insertion at the middle work. Now this method is pretty similar to insert and underscore at underscore index method we saw earlier. Let's highlight some of the noble points. So here, the method first deals with the case in which index is 0, meaning we intend to delete the first node of the list. So the code for this is ridiculously simple. All we do is change our list first underscore node to be the second node, and we're done. So here, the algorithm for that is simple. Where it gets tricky is the same with insertion, in which we're trying to delete at the middle. So the rest of the method handles deletion anywhere else from the list. So it doesn't, this code while loop, the accessing of the first index and the while loop doesn't just deal at the middle, it also deals at the end, because remember, for deleting at the end we also have end steps because we need to access first the first index. So the rest of the method handles deletion anywhere else from the list. To do this, we use a while loop to access the node immediately preceding the one we want to delete, just like in insertion. This becomes our current underscore node. So here, we then grab the node that comes immediately after the node we're going to delete and store it in a variable called node underscore after underscore deleted underscore node. So after that, we access that. Since here we first access the first index after we access the blue, therefore we're on the blue, and then we get to access the value we want to delete, or the index where we want to delete. We then get to access as well the next node using this code current underscore node, which is this that next node, that next underscore node. So notice the pattern. So we just need notice our little trick in accessing the next that node. It's simply the node that comes two nodes after the current underscore node. So since this is our current underscore node, next underscore node, we just need to get two nodes, since what we're deleting is this next underscore node. So then we modify the link of the current underscore node to point to the node underscore after underscore deleted underscore node. Then we modify the link of the current underscore node to point to the node underscore after underscore deleted underscore node. So again, we modify the link of the current underscore node to point to the to the node underscore after underscore deleted node. So we just need, or we just change this current underscore node and point that to node underscore deleted, which is the next node after the one we are trying to delete. So notice the algorithm for our deletion. It's pretty straightforward. We just change the node, there's really no removal or anything here. We're just changing the link of the nodes. So here, efficiency of linked list operation, it's the same with insertion as well. We're just changing the nodes link We're just changing the value of the node where it is pointing. So efficiency of linked list operation. The key to unlocking linked list power is in the fact that the actual insertion and deletion steps are just O1. But isn't that only relevant when inserting or deleting at the beginning of the list? We saw that to insert or delete elsewhere, it takes up to n steps. Just to access the node we want to delete or insert after. Well, it just so happens that there are scenarios in which we may already have accessed the right node for some other purpose. So the next example is a case in point. But for now, we'll get this graph or comparison. So reading for array O1, linked list ON. So search ON for array, linked list ON as well. Insertion ON, O1 at end, ON, O1 at beginning. Now deletion ON for worst case, O1 at end. For linked list, ON at the worst case, but O1 at the beginning. Worst case for ON is just at the end for linked list. So linked list in action. One case where linked list shine is when we examine a single list and delete many elements from it. So one case where linked list shine is when we examine a single list and delete many elements from it. So if you want to remove many elements, that's where the linked list shine. So let's say, for example, we're building an application that comes through existing list of email addresses and removes any email address that has an invalid input format. No matter whether the list is an array or a linked list, we need to come through the entire list one element at a time to inspect each email address. This naturally takes n steps. So if you want to come through or search for that, this naturally takes n steps. As you can see for this search, it's ON. However, let's examine what happens when we actually delete each email address. So let's see the delete operation. So with an array, each time we delete an email address, we need another ON steps to shift the remaining data to the left to close the gap, since it needs to be a continuous allocation and memory. All this shifting will happen before we can even inspect the next email address. So that's what will need to happen in regular array. You need to shift all the cells to make it compact before you do another search, which will take another n step. So let's assume that 1 in 10 email addresses are invalid. If you had a list of 1,000 email addresses, we'd had about 100 invalid ones. Our algorithm then would take 1,000 steps to read all 1,000 email address. On top of that, though, it might take up to an additional 100,000 steps for deletion. As for each one of the 100 deleted address, we might ship up to 1,000 other elements for worst case scenario. With a linked list, however, as we come through the list, each deletion takes just one step, as we can simply change nodes linked to point to the appropriate node and move on. So for deletion, we can simply change a node's link to point to the appropriate node and move on. So we don't need to ship away because it doesn't have a continuous data. So again, it's the same for search, but for combination of search and then after that is deletion, which is essentially what deleting is about. This is where linked list shine, because we can simply change a node's link to point to the appropriate node and move on. For 1,000 emails, then our algorithm would take just 1,100 steps, as there are 1,000 reading steps and 100 deletion steps for worst case scenario. So it turns out then that linked lists are amazing data structure for moving through an entire list while making insertion or deletion. as we never have to worry about shifting other data as we make an insertion or deletion. So we don't need to shift. So that's another steps. But the four basic operation, remember, is reading, insertion, searching, and deleting. So doubly linked list. A doubly linked list is like a linked list except that each node has two links. One that points to the next node and another point that points to the previous node. So essentially what it does, you guess it, you can move backward. So instead of just going forward from first index to the last index, you can move backward from last index to the first index. Therefore, if the value you're trying to get is near the last index, you can move backward. So this is the advantage of this. In addition, the doubly linked list always keeps track of both the first and last nodes instead of just the first node. Here's what a doubly linked list depiction. So here, first node. So you have 3 cells on each value or data. Now we can implement the core of a doubly linked list in Ruby like this. So we class node attr underscore accessor colon data comma colon next underscore node comma colon previous underscore node. We define initialize function and then parameter data, and add data equals to data, and then end. So we end that function and then end that this class, and then we create another class doubly linked list attr underscore accessor colon first underscore node comma colon last underscore node. So notice the difference of node attr underscore accessor. So we're accessing for a node the data, the next node, and the previous node, while in doubly linked list class we're accessing the first underscore node and the last node, and then we initialize def initialize function which accept a parameter first underscore node equals to nil, which as you can see in the depiction, the nil is the first, and then comma last underscore node equals to nil, and then at first underscore node equals to first underscore node, and at last underscore node equals to last underscore node, and end. Then we end the class. Now since a doubly linked list always knows where both its first and last nodes are, we can access each of them in a single step or O1. So since we know the first and last node, we can access them in O1 step. So just as we can read, insert, or delete from the beginning of the list in O1, we can do the same from the end of the list. So just as we can read, insert, and delete, so those read, insert, or delete operation, which is the basic operation aside from search, is better in linked list for the beginning. Now in doubly linked list, that's actually applied at the end as well. So as you can see, we can create new node Sue and have its previous underscore node point to what used to be last underscore node Greg of the linked list. Then we change next underscore node of the last underscore node Greg to point to this new node Sue. So we just need to connect that Sue, and then this last node connect to that Greg basically. Finally, we declare that new node Sue to be the last node of the linked list. So here's the implementation of insert of a new insert underscore at underscore end method that we can add to our doubly linked list class. So here, after doubly linked list, we can add this from the initialized function insert underscore at underscore end operation. This is insert underscore at underscore end, which is essentially the insert operation with the parameter value. New underscore node equals to node.new parameter value. So if not first underscore node, at first underscore node equals to new underscore node, at last underscore node equals to new underscore node, else new underscore node. So basically this first if there are no elements yet in the linked list, therefore we equate this if not first underscore node, or at first underscore node equals to new underscore node, and at last underscore node equals new underscore node. So if there are no elements yet in the linked list, if there's no elements inside, therefore this algorithm will handle that. Else So let's say we're gonna insert a value. If there's no element, therefore we will, if there's no first node yet, we will define the first node as a new node and last node is new node. That's the algorithm when there's no elements in this linked list. Else, if the linked list is already has at least one node, new underscore node that previous underscore node equals to at last underscore node. Then at last underscore node that next underscore node equals to new underscore node. At last underscore node equals to new underscore node, and then end of this if else statement. Then end of this insert underscore at underscore end function. Now let's highlight the most important parts of this method. First, we create the new node. New node underscore, it's kind of like the same, instance we create. I think it's the same with insertion. Yeah, it's the same with insertion. We create a instance value, but the difference here for insertion in single linked list is that it has only one parameter. Then we set the previous node link of the new underscore node to point to what was until this point was the last node. So we set the previous underscore node link of the new underscore node to point what until this point was the last node. So here, new underscore node that previous underscore node equals to at last underscore node. So then we change the last node's link, which was until this point. We change the last node's link, which was nil, until this point, and have it point to our new underscore node. So at last, this is actually what this means. At last underscore node that next node equals to new node. Last, we tell our instance of the doubly linked list that its last node is our new node. At last underscore node equals to new underscore node. So with the classic linked list, we can only move forward through the list. That is, we can access the first node and follow the links to find all the other nodes of the list. But we're not able to move backward as no node is aware of what the previous node is. Doubly linked list allow for a lot more flexibility as we can move both forward and backward through the list. In fact, we can even start with the last node and work our way backward to the first node, like what I've mentioned. Now, this code is pretty complex, I would admit. So we set these are were the most complex part, and the algorithm we're dealing from if there is an element in the list. So here, basically, if the linked list already has at least one node, this is what we did. Then we set the previous underscore node link of the new underscore node. So the previous underscore node link of the new underscore node to point to what until this point was the last node. So here, new underscore node that previous underscore node equals to at last underscore node if the linked list already has one element. So the previous node are connected now to the last node. Then we change the last node link, which was until this point, and have it to our new node. So essentially, these are the case in which we're handling it. In the last underscore, or in the we're inserting it. Remember, we're trying to optimize the insertion at the end. So here, we're trying to insert it at the end, where we put the previous node of the new underscore node, or new underscore node that previous underscore node is equals to at currently last underscore node. So we connect the last node to the current last node if there's one element. Then we change the last node link, which was nil until this point, since that is currently the last node, and have it point to our new underscore node. So we point that to the new node. Lastly, we tell our instance of the doubly linked list that it's our last node is our new underscore node. So at last node underscore new node. So that's where we insert that at the last node in O1. Now Q's as doubly linked list. Because doubly linked list can insert data at the end in O1 time and delete data from the front in O1 time, they make the perfect underlying data structure for a queue. We look at queues on previous video, and you'll recall that they are list of items in which data can only be inserted at the end and removed from the beginning. You learned that queues are an example of an abstract data type, and we were able to use an array to implement them under the hood. However, a more better data structure that fit naturally with queues are actually doubly linked lists. Now, since queues insert at the end and delete from the beginning, arrays are only so good as the underlying data structure. So now, since queues insert at the end and delete from the beginning, arrays are only so good as the underlying data structure. While arrays are O1 for insertion at the end, they're ON for deleting from the beginning. So a doubly linked list make the most of both worlds by having the insertion at the end. Insertion at the end, at the beginning, an O1. So a doubly linked list, on the other hand, is O1 for both inserting at the end and for deleting from the beginning. That's what makes it a perfect fit for serving as the queue's underlying data structure. So we here's a complete example that is utilize our previous code built upon a doubly linked list. So these are the class node for that we created, and then class doubly linked list, we define an initialize code which initialize that first and last node. And then we define insert at underscore n value. So the reason why this name insert underscore at underscore n, because it's inserting at the end. And then we define this new code, def remove underscore from underscore front. Remove underscore node equals to at first underscore node equals to first underscore that next node, then return node and end. So we define a class queue after this. So it's still in the same class in Ruby. Class doubly linked list, we just define inside class queue. So we access attr underscore accessor colon queue, and then we define an initialize, which is the doubly at data equals the doubly linked list that new. So we create that linked list, and then we define enqueue method, which has a parameter element, and at data underscore insert at underscore end element, and then end. So notice we take advantage of data insert underscore at underscore end for enqueue, and remove underscore from underscore front for the queue. And then we define a read as well. Return nil unless at data that first underscore node, and then return at data that first underscore node that data. And so that's defined for and reading method for front or beginning and the last index. So to make this work, we added remove underscore front method to the doubly linked list class that looks like this. So as you can see, we effectively delete the first node by changing the list at first underscore node. So we effectively delete the first node by changing the list at first underscore node. So as you can see, we store that in the variable, the first underscore node, and we remove that. We change that to the next to what is currently the second node. We then return the deleted node, return remove underscore node. So that's what this essentially removing from the beginning method is all about. So the queue implements methods on top of our doubly linked list. The enqueue method relies on the insert underscore at end method of our doubly linked list. So as you can see, it's a short code because we already have insert underscore at underscore end with a parameter element, and then we end the method. Simply that the queue method takes advantage of the linked list ability to delete from the front of the list. So the dequeue takes advantage of the linked list ability to delete from the front. So here remove underscore from underscore front, which is we just created earlier. Return remove underscore node that data. So by implementing our queue with the doubly linked list, we can now both insert and delete from the queue with at a speedy of whopping 01. And that's doubly awesome. So as we've seen, the subtle differences between arrays and linked lists unlock new ways to make our code faster than ever. By looking at linked list, you've learned the concept of nodes. However, the linked list is only the simplest of node-based data structure. So that's actually the simplest type of data structure, because this next, which is binary search tree, which will use a recursive function inside, could be, I mean, it's much more complex, and it will just get complex as we move to different data structure. In the next chapters, you'll learn about node-based structures that are both more complex and more interesting. And we'll reveal new worlds about how nodes can yield tremendous power and efficiency. Speeding up all things with binary search tree. So sometimes we want to arrange our data in a specific order. For example, we may want an alphabetical list of names, a list of products in order of lowest price to highest. So this is actually what we use. We use quicksort, but for this, while we can use a sorting algorithm such as quicksort to arrange our data into perfect ascending order, there's cost to this. As we've seen, even the fastest algorithm take O(n) log n time. So if we're going to want our data sorted often, it would be sensible to always keep our data in sorted order in the first place, so that we never need to resort it. It would be sensible to always keep our data in sorted order in the first place, so that we never need to resort it. So as we've seen, even the faster algorithm take O(n) log n time. So if we're going to want our data sorted often, it would be sensible to always keep our data in sorted order in the first place, so that we never need to resort it. So an ordered array is simple but effective tool for keeping data in order. It's also fast for certain operation, as it has O(1) reads and O log n search when using the binary search. So let's unpack this. So as we've seen, even the fastest algorithm take n log n time. So if we're going to want our data sorted often, it would be sensible to always keep our data in sorted order in the first place, so that we never need to resort it. So it may be better to use an ordered array. However, an ordered array is a simple but effective tool for keeping data in order. It's also fast for certain operation, as it has O(1) reads and log n search when using binary search. However, there is a drawback to ordered arrays. When it comes to insertion and deletion, ordered arrays are relatively slow. Whenever a value is inserted into an so for insertion and deletion, ordered array is slow, because you need to shift things away. When a value is inserted into an ordered array, we first shift all greater values one cell to the right, and when a value is deleted from an ordered array, we shift all greater values one cell to the left. This takes n steps in a worst case scenario, inserting into or deleting from the first cell of the array. So that shift takes n steps in a worst case scenario, inserting into or deleting from the first cell of the array, and n over 2 steps on average. Either way, it's O(n), and O(n) is relatively slow for simple insertion or deletion. Now, if you were looking for a data structure that delivers all around amazing speed, a hash table is a great choice. They are O(1) for search, insertion, and deletion. Not just search, insertion, and deletion, not just reading, right? However, they do not maintain order, and order is what we need for alphabetic sized list application. So what do we do if we want a data structure that maintains order yet also where we are So what do we do if we want data structure that maintains order yet also has fast search, insertion, and deletion? Neither an ordered array nor a hash table is ideal. So this is where binary search tree comes. So you were introduced to node-based data structure in the previous chapter with linked list. In a classic linked list, each node contains a link that connects the node to a single other node. A tree is also a node-based data structure, kind of like a linked list, but within a tree, each node can have links to multiple nodes, not just one, like linked list, or two for doubly linked list, but it's just the same, like two links for two cells. So here's a visualization of simple tree. So you can see you have two nodes connected to different cells. Unlike doubly linked list, though it has two connection, it's still in the same two cell. In this example, each node has links that leads to two other nodes. For the sake of simplicity, we can represent this tree visually without showing all the memory addresses. So here, JMBD. So tree comes with their own nomenclature. So here's the characteristics of trees. Now, the uppermost node in our example, the J, is called the root. Yes, in our picture, the root is at the top of the tree. It has trees are typically depicted. So, in our binary search tree, the root are depicted at the top instead at the bottom of a natural tree. In our example, we'd say that J is a parent to M and B. Conversely, M and B are children of J. Similarly, the M is parent of Q and Z, and Q and Z are children of B. So Q and Z is children of M, and J has a children M and B, and M is a parent for Q and Z, right? So as in a family tree, a node can have descendants and ancestors. A node's descendants are all nodes that stem from a node, while a node's ancestors are all the nodes that stems from. So it's pretty straightforward. Ancestors and descendants. Ancestor is your grandfather, right? In our example, or parents, or etc. In our example, the J is the ancestor of all other nodes in the tree, and all the other nodes are therefore the descendants of the J. Trees are said to have levels. Each level is a row within the tree. So these are the new concept we want to understand. Trees are said to have level. Each level is a row within the tree. So here are each level. Our example tree has 3 levels. First level, second level, third level. One property of a tree is how balanced it is. Another new concept is how balanced it is. So this is to be said that it is balanced because it has a perfectly balanced nodes or descendants for each of its or children for its parents. So a tree is balanced when its nodes subtrees have the same number of nodes in it. Again, a tree is balanced when its nodes subtrees have the same number of nodes in it. So for instance, the above tree is said to be perfectly balanced. If you look at each node, its 2 subtrees have the same number of nodes. The root node J has 2 subtrees. So this has 2 subtrees, which each contain 3 nodes. So these subtrees each contain 3 nodes, the M, the Q, and the Z, and the B, the T, and the S. You'll see that the same is true for every node in the tree as well. For example, the M node has also has 2 subtrees, where 2 subtrees each contain 1 node. So here you have 2 subtrees, which each subtree is also contain 1 node. So that's what you mean by balanced tree, in which all the subtree has the same node. So for subtree Q and Z, they both have the same node. Now, the following tree, on the other hand, is imbalanced. So as you can see, the root's right subtree contains more nodes than its left subtree. So here, B has 2 nodes, while M has nothing, right? Causing an imbalance. So binary search tree. There are many different kinds of tree-based data structure, but in this chapter, we'll focus on particular tree known as binary search tree. So there's actually more Another concept is there's another more tree-based data structure than a binary search tree. You may think that this is the only structure of tree, but it's not. Note that there are two adjectives here, binary and search. A binary tree is a tree in which each node has 0, 1, or 2 children. A binary search tree is a binary tree that also abides by the following rule. So aside from having each node as 0, 1, or 2 children, for a binary search tree to be a binary search tree, each node can have at most one left child and one right child. So there's only two nodes, left and right. Kind of like human can at most have left and right hand. So a node's left descendants can only contain values that are less than the node itself. Likewise, a node's right descendants can only contain values that are greater than the node itself. Here's an example of a binary search tree, in which the values are numbers. So the values here are numbers, but you can see the left side is less than, or the left side of its left side is less than it, and all of its node's right side is greater than it. Well, the following example is a binary tree. It's not a binary search tree. Now, it's a binary search tree because each node has 0, 1, or 2 children. But it's not a binary search tree because the root node has 2 left children. That is, it has 2 children that are less than it. For a binary search tree to be valid, it can have at most one left lesser child and one right greater child. So the implementation of a tree node in Python might look like this. Class tree node column with def the underscore init underscore function with the parameter sep, comma, val, comma, left equal none, comma, right equal 9. And then sep, we define sep.value equals to val, we define sep.left child equals to left, sep.right child equals to right. We can then build a simple tree like this. Node 1 equals to 3 node, parameter 25, node 2 equals to 3 node, parameter 75, root equals to 3 node, parameter 50, comma, node 1, comma, node 2. So this is how we can build the simple tree. For node 1, we define this as 25. For node 2, we define as 75. So node 1 is, of course, lesser, and then the root would be 50. 3 node 50. So this is how we use the 3 node class. So you can see we have node node 1, we define the node 1 is equals to 3 node 25, and then node 2, 3 node 75. For root, we define the 3 node as having the node 1 and node 2 as if as its left and right left and right children. So because of the unique structure of a binary search tree, we can search for any value within it very quickly, as we'll now see. So because of this unique structure, we're able to search for it quickly, especially for sorting application like alphabetized sorting algorithm. Or the algorithm for searching within a binary search tree is as follows. Designate a node to be the current node at the beginning of the algorithm. The root node is the first current node. So we designate a node to be the current node. So at the beginning of the algorithm, the root node is the first current node. Inspect the value at the current node. If we found the values we're looking for, great. If the value we're looking for is less than the current node, search for it in the left subtree. If the value we're looking for is greater than the current node, search for it in the right subtree. Repeat step 1 through 5 until we find the value we're searching for, or until we hit the bottom of the tree, in which case our value must not be in the tree. I think we're almost done, yeah. So say we want to search for 61. Let's see how many steps it would take by walking through this visually. When searching through a tree, we must always begin at the root. So in this case, 50. We define 50, right? Next, the computer asks itself, is the number we're searching for 61 greater or less than the value of this node? If the number we're looking for is less than the current node, look for it in the left child. If it's greater than the current node, look for it in the right child. Are you my mother? Asked the algorithm. Since the 75 is not the 61 we're looking for, we need to move down to the next level here. And because 61 is less than 75, we'll check the left child. Since 61 could only be in that subtree shown in the diagram, therefore we'll start with this. The 56 is not the 61 we're looking for, so we continue our search. Since 61 is greater than 56, we search for the 61 in the right child of the 56. Voila, we're able to find the 66. If you take another look at the steps we just walked through, you'll notice that each step eliminates half of the remaining nodes from our search. For example, we begin our search. We start at the root node, and our desired value may be found among any of the root's descendants. However, when we then decide to continue the search with, say, the root's right child, we eliminate the left child and all of its descendant from the search. We'd say then that searching in a binary search tree is O log n. So kind of like a binary search tree or binary search algorithm we've discussed, which is the apt description for any algorithm that eliminates half of the remaining values with each step. We'll soon, though, that this is only for a perfectly balanced binary search tree, which is a best case scenario. So we'll see soon, though, that this is only for a perfectly balanced binary search tree, which is a best case scenario. So the log n is only for best case scenario. Now, here's yet another way of describing why search in a binary search tree is O log n, which will reveal another property about binary trees in general. If there are n nodes in a balanced binary tree, there will be about log n levels, that is row. So this log n is actually log n levels is actually the rows, as we've discussed in characteristics of trees. Now, to understand this, let's assume each row in the tree is completely filled with nodes and that there aren't any empty positions. If you think about it, each time we add a new full level to the tree, we'd end up roughly doubling the number of nodes that the tree has. Really, we're doubling the nodes and adding ones. So to understand, if you think about it, each time we add a new full level to the tree, we'd end up doubling the number of nodes that the tree has. So if you add another level in this tree, like this, you add another this, you're doubling the nodes. Like here, when you add this, it became 4, and we add this became 8. So that's what it meant. So for example, a binary tree with 4 complete levels has 15 nodes. Go ahead, count them. If we add a 5th complete level, that means we add 2 children each of the 8 nodes in the 4th level. This means we add 16 new nodes, roughly doubling the size of the tree. It emerges that each new level doubles the size of the tree. Accordingly, a tree containing n nodes will require log n levels to hold all the nodes. Let's take a binary tree that needs to hold 31 nodes. With our 5th level, we can hold 16 of those nodes. This took care of roughly half of the data, leaving us with just 15 nodes that we still need to find room for. With 4th level, we take care of 8 of those nodes, leaving us with 7 unaccounted for. With 3rd level, we take care of 4 of those nodes, and so on. Indeed, log 31 is approximately 5. So we've now concluded that a balanced tree with n nodes will have log n levels. Since this is the base case, it makes a lot sense as to why searching a binary search tree takes up to log n steps. Because each step of the search causes us to move down a level, we take up to as many steps as there are levels in the tree. However, if you prepare to think about it, searching a binary search tree takes O log n. Now, while searching a binary search tree is O log n, So is a binary search tree within an ordered array, in which each number we select also eliminates half of the remaining possible values. So this is where the uh, ordered array, because in ordered array, in insertion and deletion, you need to shift things away. So it takes ON instead of O1. In this regard then, searching a binary search tree has the same efficiency as binary search within an ordered array. So for ordered array, searching it is actually ON. It has the same searching, but where binary search trees really shine over ordered arrays though is with insertion. So we'll get to that soon. So in insertion, actually, since the ordered array takes it needs to shift a contiguous data for ordered array for insertion. So we'll continue with the next video. Thank you.